this lesson, we're going to talk about inverse relations and functions. So we're going to start with a couple of tables. We're going to identify the inverse relation and then determine if that inverse relation is a function. So remember, when you have a table of values, the x values, which are your input, are also your domain. And the range is your y values or your outputs, okay? Now I can see from this table that this is a function. So remember, a function is when your x value is only paired with one y value. So when your input only has one output. So I don't have any repeating inputs for my original relation here. So that would be considered a function, okay? But when you do an inverse, all that happens is your x's become your y's and your y's become your x's. So if my y's are originally 1, 4, 3, 1, now my x's are 1, 4, 3, 1. And if my x's were originally -2, -1, 0, 1, my y's are now -2, -1, 0, and 1. Now to tell whether that is a function or not, we're going to take a look at those input values or our x's. And I see that I have x that has an output of -2, and this x has an output of 1. These are the same. Because the 1 is being paired with -2 and the 1 is being paired with 1, this is not a function. All right, so remember, when we do inverses, the domain becomes the range and the range becomes the domain. The x's and the y's just flip. So if we took a look at number 2, for my inverse, I'm just going to switch. So my y's were 9, 7, 5, 3, 1, and -1. So now those are my x's, and my x's are now negative, or my y's are now -1, 0, 1, 2, 3, and 4. Now remember, all of these numbers represent ordered pairs. So this is -1, 9, 0, 7, 1, 5, 2, 3, so on and so forth. So let's take a look at those x values. I have 9, 7, 5, 3, 1, -1. Nothing in my domain, or none of my x's are paired with more than one y. So yes, this is a function. So let's recall that a relation is any set of ordered pairs where x is an element of the domain and y is an element of the range. We just talked about that. An inverse relation is formed when the roles of the domain and range are reversed. So we flip-flop the x and the y. We flip-flop our inputs and our outputs. If an inverse relation of a function f is itself a function, then it's called the inverse function of f, which is written f with a little -1 like exponent of x. We call that f inverse of x. Now you can't use inverse notation if it's not an inverse, so it's really important for us to know if something is an inverse or not. So we're going to write an equation to represent the inverse of f. All right, so we are going to switch the x and the y. Now remember, f of x always represents y, so I'm going to replace y with x and replace x with y. We don't change anything else. We only flip the x and the y. If one of them is negative, you leave that negative where it's at. You only change the letters. All right, and then we're going to solve for y, so I'm going to square root both sides, and I have a plus and the minus. So y is equal to plus or minus the square root of x. Now, when you draw a square root equation, it looks like this. That would be your positive half, and this would be your negative half. If I draw a vertical line, I can see that that's going to touch 2 times. So the inverse of this is not a function, okay? So we are not going to use function notation, so I'm just going to put a little inverse symbol up on my y. And if we graph them, I do want to graph it so you can see. You have a positive root and a negative root. So let's graph the positive root of x in the first one and the negative root in the second equation. So you can see you have your positive root and you have your negative root. And again, if you were to draw a vertical line, you will see that it crosses twice. So therefore, you have an x that pairs with two y's. You can see that from your table as well. Like if I go to the point 1, 1, and I arrow over to that second equation, 1 is also paired with -1. Like that's a problem. All right, so this is not a function. All right. So take a look at number 4, and let's write that, not a function. All right, number 4, we're going to flip-flop the x and the y. So x is equal to 2y plus 1, and we're going to solve for y. So I subtract 1. That gives me x minus 1 equals 2y. I divide by 2. And make sure you divide both of those by 2. So x divided by 2, that would be 1/2 x minus 1 divided by 2. All right, and this is linear, and its inverse is also linear. Linear equations are always functions. So let's use our function notation to say that the inverse of f is 1/2 x minus 1/2. So this is a function. All right. Find the inverse of each function by identifying an appropriate restriction on its domain. So if you will recall from number 3, this is the same equation we were looking at. If you graph x squared, your original, you can see that it itself is a function. All right? It's a function. If I were to draw a vertical line, I would only hit that one time anywhere I drew a vertical line. So all of my x's are paired with one y value. Now, a vertical line test will tell you whether that function or that graph is a function. All right? A horizontal line test will tell you whether the inverse is a function. So if I draw this horizontal line, I can see that I'm going to cross that graph 2 times. All right? That means that the inverse is not a function, okay? So that means, if I have the point 2, 4 here and -2, 4, if I flip those, I now have 4, -2 and 4, 2. 4 is paired with both 2 and -2. However, if we were to take off the overlap, which would be this section over here, like this left-hand section, if we took that off, we would just be left with the right-hand section, and we no longer have a problem with our horizontal line test. So that means that we're going to say all of our x values need to be 0 and bigger. All right, we want this right-hand side of our graph. So we would restrict the domain of our original function to be x is greater than or equal to 0. So when you graph this, you have your original left side, and then you have your inverse. And then this line right here represents the mirror. So inverses will create a mirror of themselves across that line. So like if I have the point 2, 4, my inverse should have the point 4, 2. All right, they are flipped. So if I have a point here, I have a point here. If I have a point here, I have a point here. So on and so forth. The mirror should always go directly where they cross. So I can see right there my inverse and the original cross, and notice the mirror comes right through that point. That should happen every single time. Now sometimes your original and your inverse don't actually, cross on the graph, and that's fine. All right, but they still make a mirror image of each other, so keep that in mind. So let's try a couple of these. All right. Number 6, we have x squared plus 8x plus 16. So let's take a look at what that looks like. So take off whatever you had in there to begin with. So we have x squared plus 8x plus 16. All right, I'm going to go ahead and take this out. All right, so here we have another parabola, another quadratic equation. And again, if I drew a horizontal line through here, I would be able to see I'm going to touch this 2 times. So the inverse of this is not a function. So we need to restrict our domain so that the inverse is a function. So I want to take off everything that starts right here and goes to the left. So that x value right there is -4. So I want all of my x's to be -4 and bigger. I only want this section of my graph. So we're going to restrict the domain of our original to be x's that are greater than or equal to -4. So right now, I have an x here and an x here. We need to factor this because it's actually going to come out to be a perfect square trinomial. So we have two plus signs, x, and two numbers that multiply to make 16 that add to make 8 are 4 and 4. So really this is x plus 4 squared. So we're going to flip-flop our x and y. All right, and remember, we restricted this domain of the original to be x's that are greater than or equal to -4 so that we just have that right side of the graph, okay? And then we're going to solve for x here, or solve for y. So we're going to square root both sides. Now we only want the positive root, okay? So we have square root of x is equal to y plus 4. I'm going to subtract 4. So y is equal to the square root of x minus 4. Now I have to think about my domain here because my x is underneath this root. I don't want a negative underneath there. So I'm going to have to state that my x is going to have to be greater than or equal to 0 to avoid negatives. All right. So now I have my function notation, f inverse of x is equal to square root of x minus 4. And remember, we only wanted 1/2 of that root, the one that, is either top or bottom. And then we also had to restrict our domain to avoid negatives underneath the root. So this will be the restriction on your original, and then you have a restriction on your inverse. All right, so let's go ahead and think about restrictions on number 7. So if I graph x squared minus 9, all right, I can see that right here, that's 0, where it starts, it turns and goes back. So I want all of my x values to be greater than or equal to 0 so that I just have this right-hand side. So we will restrict the domain of our original to be x has to be greater than or equal to 0. I'm going to flip-flop my x and y so I can find the inverse. So I go ahead and add 9. So x plus 9 is equal to y squared. I'm going to square root. Remember, we only want either the positive root or the negative. We don't want both. All right, y is equal to the square root of x plus 9. All right, and I'm going to use my inverse function notation. All right, and then we have to restrict our domain here because we have an x underneath a root. So we do have to restrict our domain here on the inverse because x is under an even root. So we think about what would give us a negative under there. That would be -9. So I know x's have to be something to -9. So I'm going to choose a number that's bigger and see if that avoids negative. So let's just go with 0. 0 plus 9 is a +9. That would be a +9 under my root. So I want my x's to be greater than or equal to -9. All right, so we're going to sketch the graph of f and verify that the inverse will be a function and write the equation for the inverse of x. So I want us to think about domain and range before we even begin. So let's start with our original, and then we'll think about domain and range for our inverse as well. So domain and range. So for the domain, we already know that x cannot be something that would give us a negative under the root. So x is going to be something to 2 because 2 minus 2 gives you 0. So pick a number that's bigger than 2, like let's say 3. 3 minus 2 is 1. That's a positive number. So I know that numbers that are greater than or equal to 2 will give me 0 or bigger. Now 2 is the smallest number that I would be plugging in for x. So that will give me the smallest number for my range. So if I plug in 2, 2 minus 2 is 0, so I know my y values are going to be something that something to 0. Now, I know the x's are greater than or equal to 2. So I'm going to choose an x bigger than 2. Let's say, let's just go with 6. 6 minus 2, that's 4. The square root of 4 is 2. That number is bigger than 0. So I know my y's are going to end up being greater than or equal to 0. Now, because I know that with my inverse, the domain and range flip-flop, now my domain is going to be x is greater than or equal to 0 because these are going to flip-flop. And my y is going to be greater than or equal to 2 because these are going to flip-flop. All right, and we're going to be able to see that on the graph here in just a minute. All right, now I'm going to go ahead and graph this so we can kind of get a visual. So we have square root of x minus 2. If you graph this, you can visually see it starts at an x value of 2, and those x values get larger. Look at your table. It starts with an x value of 2, and the x's get larger, all right? Your y's start at 0 and get bigger. Your y's start at 0 and get bigger, all right? Now, let's do the inverse. So we have x is equal to the square root of y minus 2. So to get in there to the y minus 2, we're going to square both sides. That gives me y minus 2. We'll add 2, and that gives us f inverse of x is equal to x squared plus 2. Now, I have already stated that for my inverse, the domain has to be x is greater than or equal to 0, and that's because the range of my original was y is greater than or equal to 0, and those switched. So x has to be greater than or equal to 0. That's because when you graph this, you're going to get that U shape, and you're going to start at 0 and choose x's that are bigger. But let's graph this. I'm going to leave my original one in there. We're going to put in the x squared. Now, I have x squared plus 2. All right. And we have to show that we want to cut off that left-hand side of this graph and put in our domain. So this is what we're going to do. All right. We need to encase this in parentheses. So I'm going to go up here and insert the left parenthesis and then put a right parenthesis. And then you're going to put a division slash and then another parenthesis. And you're going to say that x has to be greater than or equal to 0. That's what we restricted our inverse to. Now, to get the greater than or equal to, we're going to go to the test menu, which is second and math. And you're going to choose option number 4 and then put your 0 and then close that up. That tells me to graph the x squared plus 2, but only graph x is greater than or equal to 0. And then I'm also going to put our mirror in. Our mirror is the line y equals x. That just kind of gives us a little visual. So go ahead and graph that. All right, now you can see it looks as though we are inverses, but it's a little bit weird looking, okay? Yours might be more weird looking. I have my zoom set to square so that my screen is more like a square instead of a rectangle. All right, you could check your points. So on this blue graph, you have a point at 2, 0. So that tells me that I should have a point at 0, 2 on my other graph. So if I go to my table and go to that x value of 0, the red graph should be a y value of 2. So you can check your points like that. So if I have a point at 1, 3 for the red, for the blue, I should have a point at 3, 1, and I do. Okay, so I do have backwards points there. All right. Your mirror, remember, is just a mirror. It's like the line that you would be mirroring across. All right, so let's go ahead and do number 9. So with cubic equations, you don't have a restriction on your domain at all because you don't have those roots. okay, even roots. You have an odd root. So we're going to go ahead and flip-flop the x and the y. And we're going to solve. So I'm going to start by subtracting 2. That leaves me with negative cube root of y plus 1. I can't get rid of the cube root until I get rid of this negative 1. So divide everything by negative 1. X divided by negative 1 is negative x, and negative 2 divided by negative 1 is positive 2. And then I have my cube root of y plus 1. So now I'll cube both sides to get rid of that cube root. Now you have 2 terms over here. You have to cube them as a whole here. So now I have negative x plus 2 cubed equals y plus 1. So I'm going to go ahead and subtract 1. And I'm going to use my function notation. So f inverse of x is equal to negative x plus 2 cubed minus 1. Now we're going to go ahead and graph these. Remember, I told you that these cubic functions, they don't have any restrictions. So let's go ahead and take out these and put in your original. So you had 2 minus the cubed root of x plus 1. And then you have your inverse, which is negative x plus 2 to the third power minus 1. And then your mirror, of course, which is the y equals x. All right, so if you look at this, right where my 2 cross, my original and my inverse, that mirror goes right through there. So it's looking pretty good. Again, you could look at your points. All right, if you have the point 0, 1, then you should have the point 1 and then 0 on your red graph, okay? But your calculator will also draw the inverse for you. So let's say I want my calculator to draw the inverse of the equation that's in y1. I can have it do that. And if it maps over the other, which would be my red graph, then I know that I am correct. So to draw the inverse, you're going to go to the draw menu, which is second and program. And then you're going to find the command that you want. We want to draw the inverse. That's option 8. So we press 8. So now your calculator just wants to know, hey, what am I drawing, the inverse of? We want it to draw the inverse of what's in y1. So we're going to press alpha and trace. That pulls up all of our little y's. So we want the y1, press enter. And then, so now you're telling it, I want you to draw the inverse of y1, press enter, and watch it. It maps over your red equation. So that tells me that what I found is correct. All right, so moving on to number 10, we have another cubic function. Remember, those are not going to have any restrictions for our domain. All right, so let's switch the x and the y. Now, before I can get rid of the cube root, I need to divide by negative 1. So I get negative x is equal to the cubed root of 4y. Now I'll cube both sides. So if I cube a negative number, it comes out to be negative. So we really don't need parentheses. Then we're going to divide by 4 and use our inverse notation. That gives us negative x to the third over 4. All right, so we're going to find the inverse and then verify that we are correct. So you can verify by graphing, but we're going to learn how to verify using function compositions, all right? So first thing that we're going to do is we are going to take and find the inverse. So flip-flop your x and your y and solve. So I'm going to subtract 5. So x minus 5 is equal to 2y. We're going to divide by 2. So I have x divided by 2, that'd be 1x divided by 2. So 1/2 x. And then negative 5 divided by 2 would be negative 5 over 2. So there's our inverse. Now we're going to verify algebraically that this is actually correct. So we're going to take and do f of f inverse of x. So we're going to take our inverse and plug it into our original. So our original is 2, and then put a parenthesis where x is plus 5. And in its place, we're going to put 1/2 x minus 5/2. And then you're going to simplify. 2 times 1/2 x is x. And 2 times negative 5/2 is negative 5. And then you have plus 5. Negative 5 plus 5 is 0, so you're left with x. This is what we want. We want an x, okay? Now we're going to go the opposite direction, and we're going to do f inverse of f of x. So essentially, we're taking our original and plugging it into our inverse. So I'm going to write the inverse down, 1/2, put a parenthesis where x is, minus 5/2. And then I'm going to plug in the 2x plus 5. So 1/2 times 2x is equal to x. 1/2 times 5 is 5/2. And then I have minus 5/2. So 5/2 and negative 5/2 cancel and leave me with x. That's what we want. If we can do the composition one way and then the opposite way, we need to get x in the end. If you get anything other than x, they are not inverses and you have done something wrong. So make sure that you check yourself, and you could also do this in your graph. You could graph and look at them as well and see if they make the mirror image. All right, we're going to use composition to determine whether f and g are inverse functions. So we're going to do the same thing that we did, only they have already given us one equation and another. They want to know if they are inverses or not. So we're going to do function composition. Now remember, it has to come out to equal x both directions. So if you do it one way and you don't get x, there's no reason to do it the other direction, all right? So we're going to start with f of g of x. So we're going to start by plugging g into f. So I'm going to write f down and put parentheses where the x is, and then I'm going to plug in the square root of x minus 5. All right, so I'm going to have to take square root of x minus 5 times square root of x minus 5. So we have square root of x times square root of x is x. And then we're going to have 2 of this middle. So negative 5 square roots of x and negative 5 square roots of x is negative 10 square roots of x. And negative 5 times negative 5 is 25 plus 5. And the only thing that's going to go together are these two to make 30. And I can't simplify that to just x. So these are not inverses. There's no reason for me to try to do g of f of x at this point. They both have to work. So if you don't get an x, then you just move on to the next one. So we're going to do f of g of x. I always start with f of g of x. You could do it the other direction if you wanted to. So I'm going to plug in for that x in my f. We're doing the 4x minus 7. So I distribute. 1/4 times 4x is just x, and 1/4 times negative 7 is negative 7/4 plus 7. But these are not going to cancel each other out and leave us with just x. So therefore, again, these are not inverses. All right, and number 14. So we're going to start with f of g of x. So I'm going to write down f. And I'm going to plug g in for this x right here. I don't need parentheses. There's nothing attached to that x there. So I have x cubed plus 1 and then minus 1. So underneath there, I'm going to add together the negative 1 and the positive 1. That cancels. And then my cube and my cube root are going to cancel, leaving me with x. So doing f of g of x works. So we're going to go ahead and flip-flop this. And we're going to plug in here. So we have x cubed, so that would be the cubed root of x minus 1 cubed, and then plus 1. So the cube and the cube root cancel. I have x minus 1 and then plus 1. Negative 1 and positive 1 make 0. And so I got x. So yes, these are inverses.